So I wanted to talk a little bit about some intuitions I've been developing since we spoke last about a way to do some more, something that is closer to what we do with Casper today. So the general idea is to modify the or generalize the cell construction. So if you remember the cell construction, you use the state actually as a kind of lock with the join, right? So you have to get this both the state and the request at the same time. So if you have the state, that means that no other requests can get into the cell at the same time. Does everyone remember that basic construction?
Yes, yes.
Okay, all right. So we could do something very similar. It requires a little bit of finesse. So let me do a screen share and show you what I'm talking about. Okay, can you see the screen?
Yes.
Yes.
Okay. All right. So what I'm going to do is I'm going to build a giant sum. So for those of you who are not as familiar with process calculi, think of this as a big select statement. And so remember that the situation that we've got in the case of the radical fault tolerance is we've got some number of copies of a race condition that's running, and we want to we want to make sure that everybody gets the race condition, the right race condition. So we have copies, say 1 through n, but in the case of Casper, each of the copies is staked. So we can associate to the to one of the roots, which we're marking with a K for the kth copy. We can associate to one of those roots a weight, right? And that weight is really associated with the validator. But for simplicity, for purposes of our discussion, we're just going to calculate the weight from the copy of the channel that we have that we're effectively intercepting, right? So what we want to do is we want to get all of those copies where the weight sums up to our threshold, right? So it's you know, the weight has to be, for example, above 66% or above 99%, whatever the sum of the weights has to be, right? That's, you think of that as our synchronicity constraint, or synchrony constraint, I mean, right? So that's, and so we're gonna have some indexes for the K, that when you sum up from I to J, then you cross that threshold, and so we're waiting on those indexes here, right? So these are all copies of the same channel that have basically been shoved into a separate namespace, right? And the namespace is indexed I through J. So that's quite a big sum, and there's a way to make it more efficient, but just to make the expression simple, I'm writing it this way. So does everyone understand the nature of the sum?
So this means that each binding represents one receive of message from one validator.
Well, but no, it's not from the validator. Remember, it's a copy of the channel where you have a race. It's indexed by the validator. It's indexed by the validator ID.
Okay. So maybe I want to. What I really want to ask is, what if validator will not send the message on this channel?
We'll get to that. Right now, we're
Okay.
going to assume perfect. Right now, we're assuming perfect communication. But do you understand how the sum works, right? So each of these
Yes.
is a copy of the channel where we have the race, and the I is the index is a validator identifier, right? And so therefore we can calculate the weight, and since we can calculate the weight, we can sum up those weights, right? And so it's any collection of these copies where the weight sums up to be more than the synchrony constraint. So we're gonna join over any such collection together with grabbing a state, right? So we're gonna get the state off of a channel that we call lock. And if we were the first one into the lock, so that's true, we will put back all of the we'll inform everyone which choice we made, right? So on the channel that we're supposed to be guarding, right, which is square root of x, as opposed to the ones that are stuffed in the validator namespaces, the actual square root of x, that will get the choice that is associated here, right? So it's more subtle than this, but I didn't have time to write down the code. But you understand all of the choices that we need to enforce, they've been enforced here. And so we know which choice we've taken. Based upon the choice that we've taken, we also know we were the first one into the lock. No one else got it. So everybody else lost. All the other collections which are waiting, they can now be notified that their ability to influence the race is done. The race has been won, right? And so now we set the state to be false. And so if anyone else gets all the data necessary to get through here, they'll get the state being false. And so, they'll know just to do cleanup. So that's basically, that is our Casper. Modulo the things about message delay. Does that make sense? Are people following along?
Yes, this makes sense.
Yes.
All right. So now in order to get the in order to deal with the message delay and message loss, we compose with the error correcting codes capability. I'm not prepared to rehash that. It's been over a year since I've had that paged into memory. But I can certainly page it back in over the next couple of days. But it turns out that you can, if you go back to the ordinary fault tolerance thing, you essentially what error correcting codes do is they're making copies of these vote messages. So you can think of the tuples that result from these things as code words. And then the error correcting codes, what they really do is they double the bits in the code words, or they increase the bits in the code words. So for example, you might triple the bits here. So instead of doing 1 out, you do 3 outs. And so then you'd case larger code words, and the larger code words deal with the noise. If the bit has been flipped accidentally by the network, the way you handle that is you treat it as if you're actually taking a vote over the votes, right? So for example, in the case of tripling just tripling a bit, right? Then you treat any 2 the same as if it were just that vote. So if your votes are either 0 or 1 and you triple it, then 0, 0, 0 goes to 0. 0, 0, 1 goes to 0. 0, 1, 1 goes to 1. 1, 1, 1 goes to 1. 0, 1, 0 goes to 0, etc. You see what I'm doing, right? You treat that as if it were another voting mechanism. So you're adding some redundancy to the code words that are being shipped out this way. So you can compose the error correcting codes with this voting scheme, and you can do exactly the same thing here. So you do an error correcting code scheme on this voting scheme here, and that will get you that will handle message corruption. You can do a similar thing to handle message delay. And so, but I can review all that. There's a well-received paper from about a decade ago that talks about all of that. So that gives you a complete spec for Casper, or at least that's a candidate. Now it's not efficient, again, because of the way this sum goes, but it's at least understandable. You can fit it on a page. So yeah, so that's a Casper. But and the important point about this is that unlike the way that Vlad and I were approaching Casper before, where we wanted it to be independent of the data that we're using Casper on, this completely sidesteps all of that, and it's totally wedded to the row calculus. So it's making essential use of the fact that we're doing this consensus over something that is the row calculus. So it's not domain independent, which was something that we were trying to do before with Casper. Does that make sense?
Yes. Mm-hmm. And can I ask you about the bindings and message delay?
Sure.
We need to have all of the answers from all of the case, right? Because we cannot proceed in the continuation. So if we have some,
if you have a delay, then that's delayed. But the way you do that is you turn it into a timeout, right? So you race that against the timeout.
But how can we extract only part of the binding? Because this is what we want.
You just add another timeout here, right? So the better approach is you race this against the timeout. So you have a timeout that's also running.
But I don't want to have timeout. I want to be able to say, oh, now I have enough messages to proceed. I have enough weight.
Yeah, sure. But the way that will work is these will all go if you got all the messages. If none of them get the messages, like if you can't get through here because one of these guys hasn't voted, then presumably someone else in the sum will have their collection of messages that can go. If nobody can go, then you're stuck, and so you have to have a timeout to break that.
Okay, I was thinking, how can we see when we have enough weight to proceed, even if we don't have all of the messages? We can say now we have enough weight and we can decide.
Oh, sorry, I misunderstood. That's what the sum does. This sum is over all possible arrangements of weight.
Oh, I see. Oh, yeah, this is what I'm missing. Okay. This makes sense. So we can have like all, yeah. I see. Yeah. We can exactly know when we have enough weight, and then we are executing this for.
That's correct. Yeah.
Okay, I see now.
Yeah, so you're looking. So this is a giant. It's like I'm listening this way, or I'm listening this way, or I'm listening this way, right? And each ways that you're listening are all the ways that you can add up the state. So it's not. It's not pretty.
So we are not even. we are not even considering this form until we have enough weight for all the messages that we are expecting, right?
Well, yeah, but or the other way to think about it is we're considering a bunch of different fours all at the same time. It's a big superposition of fours, and each four is one way that you could add up to get to the state.
I see.
Yeah.
Okay. Now it's clear. Yeah.
So this is, again, so I mean, in some sense it's not pretty. In another sense, it fits on a page and you can understand it, and we can communicate it quite clearly, crisply. Right. So the trade-offs are that this approach is very specific to row. I can't make it work for pi immediately. Right, because I'm using the fact that I have namespace operations. So it really is very, very specific to row. So that's the trade-off, but it is crisp and clear, and we can do equational reasoning with this thing. So you can do exactly what I did with this one. So so here's the definition that I did, right? And then I go through and do the calculation, right? I actually run this expression and do the calculation, and you can see that you get to the right answer. So the same thing here. You can take the sort of fleshed out version of this. You can put it in parallel. So this is the C, right? You can put it in parallel with whatever n copies of this in parallel with n copies of the process that have been appropriately namespaced. And then you can calculate, you can prove that expression will result in that everybody gets the same choice for the race. And it doesn't get deadlocked. And that's that proof. You proceed under the assumption of perfect message delivery, and then you relax that assumption, and then you throw in the error correcting codes. So this is a fairly crisp proof method, right? So in other words, what I'm doing is I'm making the proof strategy modular. Any other questions about this?
I have a question. If I'm trying to imagine like how this can be implemented, and if we are sending one deploy, so this means we have some rolling code. Do we need to do this on all branches in this code, or just on the top level?
You only need to you do it for every deploy. You run through the calculate. You can produce a new version of the deploy that is appropriately decorated together with this thing, which is the Casper constraint.
And do we need to do on all places where we have the branching, or only on the branching on the top level in this deploy? Or we are doing
it's recursive. It's recursive, right?
Okay.
It will go through everything, not just the top level. If you have a race on the inside, that's still a race, right? If in some continuation you have a race, you have to ensure that everybody agrees on the outcome of that race as well.
I see. So we are like creating some kind of version of event log directly in the rolling code.
Something like that. Something like that. Yeah.
So basically, we are directly using rolling as a protocol to exchange messages. This is exactly our message. We don't have like something else. This is
that's right. That's right. Rolling now becomes the protocol language as well as the thing you execute. Well, yeah, it makes so much more sense to use Rolling to write your protocols than something else.
Yeah.
All right. Well, if there are no other questions about this, I will turn our attention to the work I'm doing with the GSI folks a little bit. Again, I have to respect the NDA. But what I can say on our side is here's a very simple variation of our execution model. So for just for purposes of discussion, so it's a little bit more subtle than this, but for purposes of discussion, imagine that a piece of row line code, or let's say not row line, but row calculus, a piece of row calculus is really just a big par of some threads, where the threads are either, they're made up of produce, consume, and then inside that consume, there's another, par of threads that look like this, and so on, right? And so you have these little strands, right, that are all laying side by side. And so now your tuple space, it instead of storing the continuation as an object, so you can store data, right? That's reasonable. But what you really might store for either a continuation or data is the address to go and get either the value or the address to go and get the next strand of code. Does that make sense? Or not the next strand, but the next, group of strands of code, right? So it's an address that contains a block, which is each of these strands. Does that make sense? So you don't have to store the continuation, you just store the an address where you're going to pick up your computation. Is that making sense?
But still, you have to store on that address the actual continuation.
No, what you store is the address is the address refers to the block, which is, again, and it's just another block of strands of things, right? Produce, consume, right, and so on.
So this means we want to somehow resolve the nesting of continuation, so that we can put everything in like some kind of sequence. No, you don't have to resolve it, right? You're always just in the tuple space. The tuple space now just becomes a form of associative memory, right? Mm-hmm.
It's a key to an address where you can get the next thing.
This makes sense. We're basically doing this right now, right?
Yeah, it's basically what we're doing, but it's slightly different, because what we store in the tuple space is the actual thing. We store the actual continuation. We store a block of code.
Not completely clear, because we are also storing the key to another. I mean, we are storing the address where we get the real continuation.
The key is the address in our tuple space. Here, I'm saying that the key gets you to an address where you're going to go. Think of it like the address is a code pointer now. So in the case of a continuation, when you resolve that key, what you get is an address which is a code pointer, and then you just start running that code, right? And all that code will ever do is go and manipulate the tuple space, right? And either putting data or putting code pointer. Yeah, so that's the idea.
Okay.
Yeah. So in other words, if I can build that tuple space on this architecture, then we have a very, very straightforward compiler, right? It works just the way our compiler works today.
Can you say like a little more about that? Or?
So you were going to ask a question? That's super.
Yeah, well, I was. So it's still not very clear how it's different from what we have now. So now we have a cold store where we store the actual data, and we have the history where we store pointers, and we are working on the history, traversing through the history, getting pointers, reading pointers, then go to the actual data, execute these data, get back pointers, and again. So in your architecture,
yeah. So that model is very similar. But what I'm talking about is if you do just the in-memory version where you're not going off to the database, if you just do an in-memory version, what you store in the tuple space is actually you store either the data or you store the continuation, right? That's the straight up in-memory version of that.
Yeah, well, it's more or less clear. I just don't. So it's not enough knowledge I have to understand how can the continuation be stored. So there still should be some execution way to execute this continuation.
So are you familiar with like the way a stack machine works?
Well, more or less.
Okay, so
let's say less.
So think about the way a test works, right? So in the case of an if test, you do your test, and then after you've figured out whether it's true or false, then you do a jump, right? And that jump takes you to the next place where you're going to start executing.
Mm-hmm.
Right. So think about the acquiring the continuation is like that jump. So when we get the continuation, we now have a place, we now have an address which is like the target of a go-to. So we go to, and then we start executing. Now, the thing is that we won't just start executing one thread, we'll start executing a bunch of threads. But for each thread, it's just like, you know, jumping over, like if the test was false, you want to jump over the true code and go to the and start executing the false branch code. The same thing is here, right? Where we at the moment where we see that we have data associated with the key that's going to fit the continuation, then we're going to do a jump to the code that is the continuation. Does that make sense now?
Yeah, it makes sense.
Okay.
Maybe I don't understand how it will work like precisely in implementation, but this makes sense for sure.
Okay, yeah. So I'm just trying to give intuitions, right? I mean, none of it's going to make sense until we have the instruction set in our hands, and I can't really talk about that on this.
Sure.
Yeah.
But this basically what you are saying is how to store continuations in the memory in a way that in a way that we don't need to directly move it inside the memory, and we can basically just have a bunch of pointers where we can jump through the memory.
That's correct.
Something.
Yeah, exactly right. Exactly right. So now you can imagine that you've got a pool of strands to run, right? And so those are all the strands that you want to run, and then, you know, depending on how many actual processors, if you have only one processor, you run one of those strands at a time, right? And so now let's say that you're running, you've got some processor that's running a strand, and it gets to a consume, and it goes to the memory, and it sees that there is a produce at the memory, and there's a strand pool at the memory as well. So now all it does is just adds the strand pool that's associated with that continuation into the strand pool that is currently executing. Does that make sense?
Like a scheduling the next thing that needs to be
exactly
done.
Exactly. You're just adding in that strand pool.
I have a slightly related question to that. Like a question to executing rolling, and basically I see a continuation as difficult, because when we execute some continuation, we are bringing new produces and consume like into the scope of execution, and this new produces and consume, we need to compare this to existing code that we are already executed, right? Because in the initial search or for matching, we didn't see this these produces and consume, because they were inside continuation that was not executed already.
Yeah, but
So
notice if the names are free, then it's fine. And the way the scope is managed is that at the time that we add to the strand pool, we do the rewrite. Right? That's what that substitution in the COM rule is all about. You
I see.
can't add to the strand pool until after you've done the substitution.
Okay, but I think you mentioned something that is more exactly my question. So we can be smart and we can say none of these produces and consumes are not free or somehow connected to to produces and consumes that we already matched, and we can skip like doing this again. Because I'm thinking about the locking, right? We need to have some kind of locking, or
the only lock
how
is
much?
the only lock is on the tuple space.
And how? What is the minimal locking that that we need to do?
You have to be able to lock each channel, right? So when you update a channel, no matter how many threads are running, right, each channel has to have its own lock. The tuple space has to be able to support as many locks as you have threads on a per channel basis.
I see. And then if we add some additional mechanism to track which channels are for which channels we need to do again matching for the whole tuple space. Basically, I'm thinking about this nesting of consumes, how to not after each new continuation that is executed, how to prevent to search for all of the tuple space again that we already searched, if this makes sense.
Oh, I see what you're saying. Yeah, so what you could do,
like I'm thinking about some kind of optimization. Because
I
I see this as a problem. If we are like folding and like folding in parallel, and then we're basically we all, after continuation we have like new produces and consumes. So how to somehow optimize that?
Yeah, but the thing is, you don't know a priori that you're not going to the code inside the continuation that's new isn't going to mention channels that are in the rest of the tuple space. So you have to search the whole tuple space. You know, unless you've done some analysis up front, right? You don't know that it isn't going to mention all those other channels. Yeah. You can. The only time you would know that it's not going to mention the channel is if there's some kind of new scope around it.
I see.
Or if you know that they're namespaced, right? So you can subdivide the tuple space into smaller tuple spaces using namespaces.
Yeah, this is interesting. So basically, if we know some additional information about this continuation, and if we know that this is isolated, we don't need to repeat all of the channels that we already matched, because we know that it's isolated.
Yeah. So I mean, one thing is, like, if you have some kind of structure where you can slice and dice the tuple space, where you can say, you know, only give me this piece of it, and you can, you know, it's a fast filter, you know, in the same way that you can pivot you know, a relational database. So if your memory structure does that, then you could consider those kinds of optimizations. It seems like a really hard problem.
I see. But you mentioned one thing, that if we know that this is new scope, we don't even need to search tuple space. We know that this channel is completely new, right? We can just skip and say, yeah, we know that.
Yeah, that's correct. That's correct. So you can make little, but the problem is, like, making these little private tuple spaces on hardware is a little bit tough. You know, it's like you're carving out, you know, chunks of physical memory. And after you carve them out, you need to release them. So every time you introduce an optimization discipline like that, you have to also deal with your cleanup. because you've only got, so much, so much memory, right? So you have to make sure that you have a cleanup discipline.
I see.
Yeah. So.
And in a case where situation is completely clear, for example, if we have one produce and one consume, this situation is basically deterministic, right?
Yes.
No one can say, oh, there is like something else, like different common event, because we all know that only one is.
Yeah. And in a case like that, you can like, if you can prove that the code you're going to admit looks like that, which is something that we can do with the Rolang 1.1 for certain classes of communications, then you never have to do the communication, right? You just go,
Yes.
Then all you do is you put the continuation with the substitution, right? That's what you start executing. So you can optimize that away.
Does it make sense?
That's a let binding, right?
Yes. I see it now. Yeah. And in the for example, I'm thinking about event log, and we are basically like we're like labeling all of the COB events that are happened, so that we know which path is really executed. So does it make sense to only track branches where we have non-determinism? Because in all other cases, we really don't have any like, we only have one path to execute.
That's right. That's right. That's exactly right. So that, so there's, there's tons and tons and tons of optimization that we can do for row execution. I mean, it's like a cottage industry, it's like, what we need to do is get a bunch of really smart undergrads and just say, have at it, here are 3 different avenues for approaching optimization. See what you can come up with, right? I'm sure that, in 2 years' time, we could have so many clever optimization hacks that we can get, a row execution model that is like, probably an order of magnitude faster just from the optimizations.
So on the code perspective, I'm thinking, or does it make sense? Each optimization is like small little logic, and I'm thinking maybe it would be useful that we, in the code, that we can name it, and we can say, now we are using this stuff and we are implementing this optimization, and clearly it's somewhere, but because it's if it is interleaved with all other code, it's very difficult to understand which part is really just the optimization and which is like some like
I understand. And you have to make sure that you only ever introduce optimizations that play nicely together.
Yes, and I'm thinking we need to test this, so we need to maybe check all of the combinations, and so if we have one code which is doing everything, it's very difficult to extract and test these combinations. And
I agree. So there's some framework or harness that.
I'm looking from Scala perspective how to use for example, traits and default implementations to combine these two together, and we can then just mix different traits and have like different combinations.
Sure, understood.
Okay.
That's a reasonable approach. All right. Well, that's all I've got for today. So we can I'll see many of you in about 15 minutes, 14 minutes in the dev stand-up. Thanks again.
Thank you.
Thank you.
Thanks.
All right, thanks. See you.
Bye-bye.
Thank you.